Hi there, I'm Parker Glenady, and this is the first lecture in the series Comically Small Lectures on Point Set Topology. In this lecture I'll be introducing the definition of a topology, of open and closed sets, and of a basis of a topology, as well as showing a couple examples of all of these concepts. So I hope you folks enjoy. Here we go. Alright, let's begin with the definition of a topology. A topology, T, of a space X is a collection of subsets of X such that the following three conditions hold. 1. The empty set and the full set are in T. 2. If you have an arbitrary collection of elements in T, then the union over all I in I of omega I is also in T. 3. If you have a finite collection of elements of T, then the intersection over all the omega i's is also in T. That's the definition of a topology. So, in other words, a topology is a set that contains the empty space, the full space, is closed under arbitrary unions and finite intersections. It's evident from these definitions that the omega i's are quite important, so we give them a special term. Definition. A subset U of X is open if U is in the topology and closed if U complement is in the topology. Now, watch out. These aren't mutually exclusive terms. If we go back to the definition of a topology, we see that the empty set is in the topology, and its complement, the full set, is in the topology. So that means that the empty set is open and closed by this definition. This is true in any topology. The full set and the empty set are open and closed. Some texts refer to this as clopen. I don't really like this term, but we will be using it eventually. So these are very important, and it's important to just recall that things can be open and closed. They can be neither open nor closed, as we'll see soon. So let's proceed to some examples of topologies. First of all, there's the trivial topology on any set, which is equal to the empty set and the full set X. So the trivial topology on R is the empty set and R. It's trivial in the sense that it's the simplest to define. It doesn't really tell you much about the structure of any set, but it will become very important as time goes on. Then there's the discrete topology, which is equal to the power set of X, which I write 2 to the X, and that is equal to all omegas such that omega is a subset of X. This is the discrete topology. It's a topology since the empty set is in it, the full set is in it. The union and intersection of sets in X is a set in X. So evidently it's a topology. Some less trivial topologies would be the particular point topology at P, which is equal to the set of all omegas such that P is in omega, which is a subset of X. Now, this isn't a topology yet because P is not in the empty set, as it's empty, so we union on the empty set. This is now a topology, since the union of sets that contain P contains P, the intersection of sets that contain P contains P. And this is the particular point at P. Yes, and now we can do the excluded point topology. which is equal to the set of all omega such that P is not an element of omega, which is a subset of X. In this case, we have to union on the full space, since P is in the space, and this is the excluded point. At P. It's also a topology because the union of sets that doesn't contain P doesn't contain P, the intersection of sets that don't contain P does not contain P. So it's easily verified that this is a topology. I leave it as an exercise to you to go out and, rigorously prove all of these things. I've just kind of run through the sort of idea for you. Okay? Now we're going to move on and talk about the basis of a topology, which will be very important and will allow us to cook up a variety of topologies on sets such as R, and in more abstract spaces as well. So, definition. A set B is a basis if 1. For every x in X, there exists a Bx such that X is in Bx. Yes, so Bx comes from the set B. And 2, for every B1 and B2 in B, there exists B3 in B such that B3 is a subset of B1 intersect B2. Now that can be equal to it as well. Now we say now the set B is a collection of subsets of X again, and we say that it generates, then B generates a topology TB on X where TB is equal to the set of all unions of things in B. Now, in the next lecture, we'll prove that this is actually a topology, but you can try this at home. The criteria that every X is in a Bx is very important for satisfying the first criteria of a topology, and the second criteria is very important for satisfying the third criteria of a topology. So, I hope you folks have enjoyed this lecture. Talk to you soon. Bye-bye.